So let me introduce our speaker. Firstly, thanks very much to everyone for coming today to the latest Spatial ML seminar. Just to flag that this is the last one of the calendar year, and we'll be resuming the series in January. So for the last seminar of the year, I'm delighted to welcome Sulaiman. Sadiq. Sulaiman is a PhD student at the University of Southampton under a Minds CDT studentship in collaboration with Arm Limited. He holds a BE in electrical engineering and two MScs, not just one. Two MScs, one in computer engineering and one in artificial intelligence. He also has 6 years of experience in industry, working on real-time embedded systems in the R&D sector. His current research focuses on enabling deep learning inference on microcontroller devices by optimizing across the software stack through efficient inference software and model design. So very much central to our interests here, and I'm very pleased to welcome Sulaiman. Please begin.
Thank you, George, for the introduction, and thank you, Andrew, for arranging all of this. So the work that I'm presenting today is based on our paper that was recently accepted in the Internet of Things journal. So it's enabling ImageNet-Scale deep learning on microcontrollers with accurate and efficient inference. So the work was performed by myself, Sulaiman, Sadiq, and I was supervised by my supervisors in Southampton, Jonathan Hare and Jeff Merritt, and on the ARM side, Simon, and with Partha, who is now at TensorTorrent. So just a brief introduction on the work. So with the ever-increasing number of IoT devices, there has been recent increase in getting AI onto edge devices. And this has led to the development of the field of TinyML. And TinyML basically aims to develop models and frameworks which are able to process data locally on device. And this is desirable for a number of reasons, which includes security and privacy, connectivity, power consumption, and latency, which is associated with the traditional cloud computing paradigm. So, but if you want to do this locally, there's a couple of challenges that are associated with this, which is that deep learning, typically it's done on cloud or mobile GPUs, and these devices have a much different architecture to microcontrollers, which are bare metal devices. They have a much simpler architecture, so where a GPU might have thousands of cores, the microcontroller just has a single core. It has much smaller internal memory and storage, and there's no operating system. It has a flat memory model and no sophisticated memory management. So a bit of background in terms of how exactly people do deep learning on microcontrollers at the moment. So the standard thing, if you want to deploy a model on a microcontroller, you're going to train it in a high-level framework such as PyTorch or TensorFlow, Python-based frameworks. And you can quantize this with a high-level framework as well. The go-to is TensorFlow Lite, and usually you kind of go with integer 8 quantization. And in this high-level framework, you can kind of serialize your model as well. And the format for that is like a flat buffer format. And when you serialize this model and quantized it, you can then deploy it onto your microcontroller. And you would deploy this with a low-level framework, and examples would include TensorFlow Lite Micro, MicroTBM, or STM-Cube AI. So in our work, we focus on TensorFlow Lite Micro. It's probably the most mature and very popular and widely used framework. It's open source, and it's an interpreter-based framework. So an interpreter-based framework would be that if you have an inference graph, you have a framework that is going to interpret the inference graph and kind of run through the inference graph and sequentially perform all of the operations in the graph. And these TensorFlow Micro, the TensorFlow Micro framework, we use this with CMSIS NN kernels, which is the Cortex machine learning software interface standard for neural networks. And these are a compilation of high throughput kernels that have been developed for ARM MCUs, which are the devices that we target. So looking at the basic architecture of a microcontroller, just a kind of block diagram. So you have a CPU, single CPU, and this will have access to some on-chip memory. This is usually going to be SRAM, which is less than 512 kilobytes, and on-chip flash, which is less than 2 megabytes. In addition to that, you have some external memory interfaces that you can connect to with the flexible memory controller over here, or with the quad serial port interface. And quite typically, you have a direct memory access or DMA peripheral on these devices as well. So in internal memory, internal memory usually has low power consumption. It's very fast, but it's quite limited. On the other hand, external memory, it has higher power consumption. It's large, but it's slow. So for edge inference, prior works mostly focus on internal memory. And the challenge over here is that if you take state-of-the-art models derived via NAS or handcrafted, uh, the amount of storage and memory that they require is typically much larger than you have available on microcontroller platforms. So how do prior works kind of go around designing models for the constraints of internal memory? So within these internal memory constraints, prior works either focus on scaling existing mobile models. So the conventional scaling approach is that if you have a baseline model, you can either reduce or increase the width. In this case, it's being reduced. Or you could reduce the resolution to decrease the amount of memory that you require. Whereas width would reduce the number of parameters that you have, so that would reduce the amount of storage that you need. So an example of this, and the nomenclature that we're going to be using in this presentation, is something like this, which is that if you have a baseline network such as MNASNet with a width of 1.0 and a resolution of 224, you can reduce that to a quarter of the width, which is 0.25, and reduce the input resolution from 224 to 160. Another thing that's fairly common is quantization. So you can lower precision from floating point 32 to, say, 4-bit or 8-bit into 8 quantization. Quite often, the industry standard is just to go with int8. And the reason for this is that this is the data type that is supported by as an operand for the instruction set, which is native to the microcontroller processor. Apart from scaling, quite often what the works do is neural architecture search. So just designing a model using automated algorithms under the constraints of memory and storage, and they just kind of take that memory consideration into the search algorithm loop, and that helps them find an architecture. Or some works are also come up with memory efficient inference kernels. So that also helps with fitting a larger network. So in our work, what we did was that we analyzed models designed for diverse internal memory constraints of a number of devices, and found them to be suboptimal for accuracy, which is kind of understandable because you have a smaller model, so you would expect the accuracy to be lower. But we found them to be suboptimal for latency as well, which was kind of interesting because you have internal memory, the models are smaller because of the size limitation, and internal memory is faster, so why was the latency higher? So we kind of dug into this a little bit, and we found two main limitations. The first is that we found that these internal memory models, they fall below a Pareto frontier. And the second is that when you go out to actually deploy these models, the models were actually doing a lot of computation in inefficient operations for MCUs, which was leading to higher latency. And I'm just going to go into detail for both of these in the next couple of slides. So to study these internal memory models, what we did is that we approximated a Pareto frontier with scaled variations of a mobile model. So in this case, we used a backbone network of a proxyless NAS model. And for different widths, we varied the resolution from 48 to 224. So for a width of 0.3, we get this curve over here. For an input resolution of 48, and kind of incrementing that in increments of 16, going up to 224. Similarly, for width 0.5, and with 0.75. And we compared this with models derived for the diverse internal memory constraints of ARM Cortex MCUs. And these devices over here, which is based on the Cortex M33, M4, and M7. And the internal memory models that we kind of compared with or studied were scalings of mobile models derived for internal memory constraints, and architectures derived via NAS for internal storage and memory constraints. So for the scalings of mobile models, we found these to lie below the Pareto frontier over here. And the neural architecture search models, we found them to have higher accuracy, but also a lot of computation. So why exactly does this happen, and why do they lie below the Pareto frontier? Well, because the reason is that when prior works derive models via conventional scaling, they use the highest width and the resolution possible to achieve the maximum accuracy. But if we study the Pareto frontier, what we find is that there is a point of diminishing returns over here and over here. And we find that for any particular width multiplier, such as this for 0.3, increasing the resolution past this point is suboptimal because you can just, instead of increasing the resolution, you can just swap over to using a higher width. So at this point, using the width of 0.5 is optimal, and past this point, a width of 0.75. However, due to the constraint of internal storage, these previous works that focus only on internal storage and memory can't actually go to this width of 0.5 because they're constrained by the amount of internal flash that they have. So for a number of constraints or a number of models derived via this conventional scaling approach, we see that these models lie well past this point of diminishing returns here and over here, and similarly this one and this one over here as well. So what this would imply is that if you want to make any back budget, this would require like the right balance between width and resolution, and simply using the highest width and the highest resolution kind of gives you suboptimal results that lie below the Pareto frontier. On the other hand, these NAS approaches, which are this purple, red, and brown point over here, we analyze these, and the answer to why these are suboptimal lies in the search algorithm and the objective that is maximized to get maximum accuracy. So these approaches, what they do is that within internal storage and memory constraints, they maximize computation, which is max, in the model, and they take this as a proxy for accuracy. So the way this is accomplished is that they reduce the parameters in memory-intensive classifier, which is at the very end of the network, and the parameters that they save from this classifier, these are used in the compute-intensive convolution and depthwise convolution operations. And along with some other changes to microarchitecture, they find that what they show is that they are able to maximize the compute in the network under the same internal storage and memory constraints. And this does give a increase in the accuracy, but it comes at the significant cost of significantly increased computation or max. And this results in high latency as well, or high computational complexity. So this is when we're considering the accuracy max Pareto frontier. When we actually go to deploy these models, we found them to be further kind of suboptimal when you go and implement these models or deploy these models on MCUs as well. And for the scaling approach, we found that when you use the conventional approach of scaling down to meet internal storage memory constraints, so what that does is that it focuses computation in inefficient depthwise convolution operations. So what we did was that we analyzed kind of analytically how the distribution of computation changes when you reduce the width. So we looked at the structure of the architectures derived from the mobile search space. And these contain cascaded mobile inverted conv blocks. And these have a structure like this. So in a architecture derived from the mobile search space, you would have, say, 10 of these or 20 of these cascaded together with the input channels, the expansion ratio over here, and the output channels, and the filter size. These are selected as hyperparameters, and which are either chosen manually or derived via the NAS algorithm. So if you look at this module over here, if we reduce the width by a factor of alpha and the resolution by a factor of beta, the way the computation is scaled down, we can look at that in these equations over here. And what happens is that if we see in the convolution operations, there's a quadratic reduction in the max, whereas in the depthwise convolutions, there's only a linear reduction in the max when we scale down the width by a factor of alpha. However, if we scale down the resolution by a factor of beta, it's reduced quadratically in all three operations by beta squared. And what this does is that from a baseline network, if we progressively lower the width from 1.0 to 0.65, 0.5, 0.3, This has the effect of progressively focusing or skewing the distribution of computation such that more computation is focused in depthwise convolution operations. And we can see that over here. So we go from 0.65 to 0.5 to 0.3, and the percentage of computation that's focused in depthwise convolutions increases from 18 to 22 to 29. On the other hand, if we meet any particular Mac budget by, say, reducing the resolution by a factor of beta, so we can go from 224 to 160 to 112 to 180. So we can reduce the max or the computation in the network, but the distribution remains constant with an 87% in the convolution operations and a constant 13 in the depthwise convolution operations. So why would this be an issue? Well, what we did is that we benchmarked the throughput of these operations. And we looked at 3x3, 5x5, 7x7 depthwise convolutions, and convolution operations. So these were sampled from different networks and they have like operations have these different filter sizes, different input and output channels, different input resolutions. And then after sampling these and seeing what the latency for each of these individual operations were, we fitted a best line to each of these, best fit line to each of these. And what pops out is that convolution operations are much more efficient than depthwise convolution operations. And another observation that we make is that within these depthwise convolutions, 3x3 depthwise convolutions are the most efficient. So if we look at this diagram again, so this is max over here, but when we translate this to latency, what we find is that for the same Mac budget, if you meet the Mac budget by reducing the width or the resolution, meeting it with the resolution, with a low resolution, results in faster inference latency, purely because you're doing the same amount of computation, but the computation is performed within a efficient operation. But of course, so this would imply that, okay, so you should always use the highest width possible, and that would result in lower inference latency. But again, the constraint of internal storage doesn't really allow that. Similarly, like for NAS-based approaches, we found that the neural architecture search approaches maximize computation in the network in an operation-agnostic manner. So they didn't really look at whether the computation was being performed in 3x3, 5x5, 7x7 depthwise convolution or simple convolution operations. And those networks, again, had a significant amount of computation focused in these inefficient operations. Okay, so having identified the limitations, what we propose is that, can we alleviate these constraints? So we propose like using external memories to alleviate the internal storage and memory constraints. However, the issue is that external memories are slower, and this leads to higher inference latency and a suboptimal Pareto frontier. Suboptimal accuracy latency per Pareto frontier. So these models, all of these, if we just simply kind of these with 0.5 and with 0.75, if we deploy this with external memory, then this Pareto frontier ends up over here. We get this discontinuous Pareto front. So the question is, how can we kind of get this back over here? How can we replicate this Pareto frontier, the accuracy max Pareto frontier, in the accuracy latency domain? So for this, we developed the TinyOps inference framework, which combines the advantages of external memory, which is design flexibility, and internal memory, which is speed. And what the TinyOps inference framework does is that it accelerates external memory inference latency using a partitioning scheme and DMA-based overlays. And this allows us to perform inference of large models in external memory with internal memory like latency. And this partitioning engine that we use, we build this TinyOps basically on the TensorFlow Lite micro framework. And the TinyOps partitioning engine just kind of slinks into the software stack quite simply. So how does this work? How does the TinyOps inference framework works? So the standard way that TensorFlow Lite micro essentially performs an operation is that if you have an input tensor and output tensor, the entirety of this is declared in memory. But of course, the issue is that this is too large for internal memory. So what we change that to is something like this. We declare these tensors in external memory and kind of logically partition them into a couple of tiny tensors. And the internal memory, we use this just for a couple of fast buffers that we keep in internal memory. And these fast buffers, the size of them is big enough so that they can fit these logical tiny tensors that we have in external memory. And we can then use kind of offload the data fetching from external memory to internal memory to the DMA. And that's shown over here. So X2A is copied into B1, and then B1 is processed, in this case, by a average pooling operation, which is performed by the CPU. And while this is being done, we can kind of have to use this a double buffering strategy where the DMA starts copying in the second chunk of data that needs to be processed into B0. And when the data, by the time essentially the CPU is done processing the first tiny tensor, the second tiny tensor has been copied in by the DMA. And when the CPU starts processing the second chunk of data, the DMA can copy the third chunk of data, and essentially so on and so forth. Using this double buffering strategy and establishing this pipeline between the CDMA and the DPU, we can effectively hide the latency of fetching data from external memory. So just to look at some numbers over here. So TinyOps compared to just naively performing inference from external memory, the latency is reduced by 1.3 to 3 times. And compared to internal memory, so if we have a model over here that has 855 milliseconds, we get a slight overhead, 9 to 77 milliseconds, or 1089 to 1131, but it's like in the comparable region. With regards to power, because now we're using external memories, we do have higher power consumption, but we believe this can be offset by the efficiency of models in the TinyOps design space, so that would enable us to achieve lower energy per inference. Yeah. So what the TinyOps framework allows us to do is that it accelerates inference through external memory, and essentially it pushes forward this accuracy latency Pareto front. So when we deploy all these models with TinyOps, we get the Pareto frontier over here. And now we can simply pick up models from this Pareto front over here and deploy them to achieve higher accuracy and better latency as well. So from the insights gained from our study, what we can do is that we derive efficient models from the TinyOps design space. So by studying this Pareto front, we deploy balanced scalings from the Pareto frontier. And we use scalings from the MobileNet V3 model. And the reason we do this is that because it only uses efficient 1x1 convolution and 3x3 depth-slice convolution operations. So deriving these models, we compared models derived from the TinyOps design space with the internal memory models derived for a variety of internal storage and memory constraints. So what we find is that the MobileNet V3 scalings from the TinyOps design space outperform the NAS and scaling-based approaches. And over here, we can see, for example, this MCUNet V1, this one over here, this MCUNet V1 model derived for the F746 with 8-bit quantization. We can outperform this with the MobileNet V3 architecture, a scale variation of this with 6% higher accuracy and 1.4 times faster latency. And these 4-bit models that were derived by this MCU network. So over here, the latency wasn't reported, so we kind of compare with Max, but we could get about 6% higher accuracy with around 24 million lower Max. So these MCU models, they're from the internal memory design space, but due to the unavailability of the MCUNet inference framework, we had to deploy these with the TinyOps framework. But to compare the energy, we compared with these scale variations of proxyless NAS models as well, which achieve the highest accuracy. Over here, we can see that for this F469, the optimal scaling of a proxyless NAS model for internal memory is outperformed by a MobileNet V3 with 2% higher accuracy and around a 1.6x faster inference latency. Even though it has like a higher power consumption over here, it results in a lower energy per inference, about 1.1 times lower. So just to summarize, so we demonstrated the limitations of deriving models from the internal memory design space of MCU platforms. So we proposed relaxing the constraints with external memories and accelerating inference with the TinyOps frameworks. And we showed that efficient architectures from the TinyOps design space achieve record TinyML ImageNet classification with up to 6% higher accuracy and 1.3x lower inference latency. Sorry, a bit of a typo over here. Yep, thank you. Take any questions.